So hello everyone. I don't know how many of you guys have been in the other room with Neil and Jan presentation. Yeah, so he stole all of my jokes. Not many in this presentation, but they are gone. So sorry for that. This will be a set presentation. All right, so yeah, Apache Spark 101, and the clicker is not working. Awesome. Yeah, okay. My email, if you fear to ask questions, then just write me an email. If you guys tweet, then please include me so I know your opinions about this presentation. The thing with this presentation is that it was originally designed for 1 hour and a half, and I had to squeeze it into 50 minutes. So I'll ask you guys some questions, like whether you understand MapReduce or not. I will not anticipate answers, just like yes or no, so I know whether I can skip through some slides or not. All right, so the very first question here, why are we here? What's the point of being in this room? And you guys will tell me, Spark. Well, I know Spark is a tool. Why do I need this tool? And the answer is one word, big data. Yeah, it's one of those jokes, because can you guys tell me what actually big data is? The very definition.
Buzzword.
Buzzword, yeah. But the one that I truly find, well, I find one on Twitter, and I really like it. And basically, the definition is like, big data is actually like teenage sex. Everyone talks about it. Nobody really knows how to do it. Everyone thinks everyone else is doing it, so everybody claims they're doing it as well. So that's actually a problem of big data, because if you want to be a cool kid on the block, you have to be doing big data. But eventually, we are doing big data in our industry, and if you're doing big data, then you need some tools to actually run it and not go insane. And but if you want to find the very definition of big data and why do we need tooling for it, then I think the definition of big data is basically big data. That's it. Well, it's all about data. Right now we are currently creating mass amount of information. For me, I don't even understand this number. I mean, like, come on, what does it mean even? I like this guy who said that right now every 2 days we create more information that we've created from the beginning of humankind till the year 2003. That's like insane. How is that even possible? How is that even possible? Like, within 2 days, we just created more information that the whole humankind created from the very beginning? Well, the answer is selfish, right? But nevertheless, it doesn't matter how do we create big data. The thing is, we have to somehow deal with the big data, because the challenges that we will have are new. When you have a cluster of computers and you have data that you possibly cannot fit into one computer, you have to switch somehow your mindset to deal with those problems. There's no such situation right now that, for example, your computer will, well, my database isn't working, sorry, so it's a DevOps problem. No, right now if you have clusters of like hundreds of computers, it's just a normal situation, like one of the nodes is rebooting or not working, or there's a latency problem in the network, whatever. So the tool set that you need has to deal with all those kinds of challenges. But it's not a new problem. Big data, it's not suddenly that we have to go reactive like since yesterday. It's not a new concept. And there were tools before. 10 years ago, we were introduced to MapReduce, a research paper from guys by Google. So how many of you guys are familiar with MapReduce? They have to explain it. All right. Most of you guys. That's cool, because we'll be able... Unfortunately, my computer isn't compatible with this thing here. So my video with my demo is not working on this Mac, so I'll have to probably improvise, but we'll see. Nevertheless, MapReduce, the basic definition, I'll just quickly go through the basic definition, but you guys are pretty much aware of it. So we have two phases of sequences of map and reduce. I probably don't have to explain what map and reduce is on the Lambda Days conference, hopefully. Right? Okay. I hope yes. The problems, it's a slide for people who actually didn't know what MapReduce is. With implementation in Hadoop, so it runs on key value pairs. You don't have a collection of values There's always a pair, like a key and a value, and you operate on those. All right, so the word count, which is the very hello world of big data. We have our input files with lines of text, and we want to count the occurrences of each word within our input file. I feel like a star. Thank you. All right, so how it works in MapReduce. You have your input data here. Then what you will be doing is splitting that data, partitioning it throughout the cluster. So it will be, data goes through to all the nodes within your cluster. Then there will go the mapping phase. In our example, what we're essentially doing is we're taking each line, we split that line into our words, and we are emitting a pair where the key is our word is a key, and the value is simply 1. There comes another phase called shuffling. This is the most expensive part of the whole cycle, because what essentially happens is that all data travels through all the network around the cluster, putting all values with the same key into the same node. So that's if you're running like petabytes of data, that's the most important, crucial part, which will, if not done properly, you'll have performance issues. And at the very end, you have this reduce phase. In our example, it's like simply taking all values and summing them up. And at the end, we have a final result. Is that comprehensible? Is it okay? Yeah, so quite simple. And this is a code taken from Wikipedia. So as you can see, I'm taking document. For each word in the document, I emit a pair with the word and the value 1. And I reduce. Probably not the best example for guys who are doing functional programming, but it works, right? It works. We just simply add all those values 1, and we have our final result. So the question again is, why are we here? It works, right? We have Hadoop for like 9 years. MapReduce was introduced 10 years ago, so it's a decade of working, mature framework. So why the hell Spark? All right, so apparently there are problems with MapReduce, and with Hadoop in particular. The very first problem is a difficult programming model. And you should be all like, what? And this is easy, right? I mean, I know it's not the best functional code that could be. Probably there could be some optimization here, but it's easy to read. The only problem is it's a pseudocode from Wikipedia. But if you Google word example in Hadoop, you will run with this. And that's not the whole code. It actually finished somewhere here. All right? That's not readable at all. Second thing is, So Hadoop tried to address that problem. They said, well, let's take a declarative language, SQL, and we just give our programmers the declarative language that they understand. They will just simply tell us what they want to achieve, and we will give them the equivalent running MapReduce phases, and everything should work just fine. The only problem is that even the simplest query that you will do on Hive, which is like count distinct occurrences within your data set, will give you 2 phases of MapReduce. And if you know anything about it, you know that shuffling operation is very expensive. Each phase, switching to another phase, is the most important, most expensive part in the whole computing. But they say, okay, that's not a problem, right? Because it's 9 years of Hadoop running in our production code. So we have already books like best practices and cookbooks and things like that. And you will learn that that's not actually not a problem, because you can do something like that, and you end up with like just 1 phase of map and reuse. But at this point, do we still have the declarativity? Because if I have to run my SQL query, and every time I have to see what actually is running within my Hadoop cluster, then I would just rather write a Hadoop program, and that's it. All right, so another problem is that actually Hadoop and MapReduce suffers performance issues. And you guys should be like, what? That's an oxymoron, right? Hadoop? Performance issue? No, it's blame fast. Apparently it isn't. So there are many problems with Hadoop. The main problem is with Hadoop. Each time you will do MapReduce phase, all your output data will be saved on the disk. It goes all to I/O. Even if you go and run the another computation with that data, it will be saved within your cluster. That's slow. If you have a batch processing algorithm, like you read your data, you create some report for your business, and that's it, then you'll be fine. But if you have algorithms that have to go on and on with data, and you have to read them every time, that's also a pain. And also the API, the key value pairs, makes the simplest queries like joins a pain as well in point of the performance. And the last but not least, we are at the Reactive Day, Reactive Day conference, right? We know that everything now has to be real time, almost real time. With batch processing, with Hadoop, well, you can for example choose, let's say Apache Storm, but essentially you will have your batch processing done in Hadoop. You will have your real-time processing in Apache Storm, and bugs can happen in this code and in that code, and maintenance might be a hell. So you have to be aware of that. All right, so I just gave you some set of problems with MapReduce. Now Spark to the rescue, all right? So the very first problem was not intuitive programming language, so I introduce you an intuitive programming model. All right, so word count one more time. We will look at word count right now from the point of Scala developer. And I come from the Java world. I'm actually developing Scala for only half a year of my professional experience, of only half a year. So I'm like, oh my God, this is a Java developer. Throw tomatoes at him. No, sorry. So this example might be the best. So if you guys see any optimizations in that code, please tell me. But actually, that's not the point of this slide. You will see in a moment why. So let's do a word count in Scala. So I will take my iterator of lines. I will map that into lower cases. I will split each word to have a collection of those words. I will group by word. And at the very... Where's my... Oh, no. Oh, no, please do work. Yeah. So at the very end, I will map that into like my word and occurrences of that word. Now let's see how it works in Spark. So that over here was just simply a code in Scala. What we'll be doing right now, we'll be seeing an API of Spark in Scala. Just not right now. You don't have to go into details. Don't try to understand everything. Just try to feel the mode of programming in this API. So the same thing happens. We collect our text file. We collect some kind of interface to that, some kind of abstraction to that file. We will, oh, come on. We will lowercase that each line. We will split each word. We will group by this word. And at the end, we will return a pair of word and the size. And just a quick info for guys who are actually developing stuff in Spark. They know that using group by is not the best thing to do. I can tell you later on why. But then again, you have an API. It basically looks exactly the same as the code you would write in Scala without using Spark. So I hope, well, this is easier than what I showed you in Java. I hope. Yeah. All right. So I introduced problems with Hadoop. I will try to show you how Spark actually try to work around those problems. So, performance boost. Imagine that we have a cluster with 3 nodes. Let that be our representation of our cluster. And we would like to do some calculations on the data that we have. It will be like some kind of batch processing right now. So I want to do some mapping. Maybe later on I will group by my data by some key. Then I will do mapping one more time. I will reduce by key. And I will have my output, my calculation. So what Spark actually does, it sees that, well, we have some calculations on our data. That data is already partitioned within the cluster. So it can take that calculations over here and just start pipelining, running them on that very first node. without actually other nodes even starting up. And it will do with each partition, it will actually run the same code over here with each node in parallel. Because at this point, those guys do not need to talk to each other. At this point, they are just running parallel, and it doesn't matter if the other guy is winning or not. I don't care. But there is a moment before group by that you need to have all the data mapped to actually group by. You have to wait here at this point to all the data to finish the calculation on each of the node. And then again, you have another set of tasks. Those guys can run in parallel as well. So in Spark, those phases are called stages. You have stage 1, and you have stage 2. And you can essentially think about stage as the super calculation. So it takes your set of your calculations, Spark scheduler will see, okay, I can actually run it in parallel within the cluster, and it will just run those calculations, wait for results, and then either push the results to another stage or just return results to your program. And you guys might think, well, that's MapReduce, right? I mean, phases, it's exactly the same. Well, it isn't. First of all, you have to remember that you can do whatever programming thing you want here as long as you are able to pipeline, so map, filter, all that stuff you can do, as long as you can pipeline those things within one node. And there's another issue that you should be aware of. Imagine again our example. We have some our initial input. We did some mapping, some filtering. And at this point, we group by some key. Our data is partitioned, and the Spark knows by which key. It holds that information over here. If we introduce another set of data, and we will do join between those two data sets, what will happen? Well, first of all, it will be joined by the same key. It will be joined by the same key that we did actually group by over here. So, well, at that point, shuffling mechanism has to start. It's essentially to have all the data within the same node. You need to shuffle all the data from other nodes to, all keys from those go here, here, and here. But that data over here is already partitioned. Spark is aware of how the grouping by went. So it will be not doing shuffling. It will work just like this. Actually, it will work other way around. This guy over here who will be doing the joins will see, okay, this is already partitioned, so I'll just put all the data according to how this data set is partitioned. And that's actually is one of the biggest boost performance in Spark. That's what kicks the performance in Spark. You might hear that caching mechanism is the one that's actually giving Spark its boost. That's why Spark is so fast. Well, it isn't. It's one of the mechanisms, but it's not the most important one. If you could just give me a second. I have a sore throat, and I was drinking beer yesterday. I was so stupid. So sorry for that. I blame some of guys who are sitting here. It's their fault. All right, so let's imagine a simple algorithm like PageRank. You guys know PageRank? This picture is taken from Wikipedia. I don't like this picture. I like this one. I will not go into the algorithm because I hope most of you guys know, but for those guys who don't know how PageRank works, basically it gives you ability to rank whatever graph you can think of a graph, nodes, edges, and things like that, like pages. And it works in a way that I'm more important within the graph if more guys are pointing at me. And if some really important guy is pointing at me, then at the same time, I'm also important. So to actually calculate PageRank, you have to go through each of the nodes within the cluster, do some calculations using some calculations defined in PageRank algorithm, but you have to do it sequentially some number of times. There's a like stop point where you stop, but eventually you have to do some few loops within the algorithm. So you have to read the data, do some calculations, then again read the data, do some calculations, and eventually stop. So Spark introduced a caching algorithm, which allows you, so if you load your data within your cluster from HDFS files or whatever from your database, it doesn't matter, you have ability to actually persist that data within your memory. So you load your data for the very first time in the PageRank algorithm, you persist that data within the memory of your cluster, within the memories of each node of your cluster, working nodes. And then, if you rerun the calculations one more time, this time they will be not read from the input source, like database or HDFS file. They will be already within your cluster and already in the memory. So this gives a kick. This is actually taken from Apache Spark webpage, and it's running PageRank algorithm. So you see that, Hadoop is like, okay, I will just start this algorithm, and it's like, I'm done. I'm going for a beer. So this really kicks off if you have those kinds of algorithms. But if you go to forums like Hadoop forum, posts like which are right now maybe 1 year old, you will see those guys asking on the Hadoop forum, listen guys, there's this Apache Spark. Suddenly everything is cool about Apache Spark. Do you guys know anything about it? And those guys will tell you, no, Apache Spark is only when you have data that will fit into memory. If it will not fit into the memory, it will not work. Well, this isn't true. The caching mechanism, first of all, it might be configured to cache some amount of data into your memory, and also, oh come on, go away, England. It might cache some part of your data into the memory, and also it only gives you boosts if you're doing recurring algorithms. If you're doing patching, that you're not even using this functionality at all. But just to prove a point, guys from Apache Spark, they ran into this sort benchmark. It's a district benchmark that basically you have to sort data. It's 100 terabytes of data, 1 trillion records. It doesn't state how many machines you have to use. It doesn't state what kind of machines. Basically, the result is the fastest, the better. And in 2000, I believe in 2013, the record was in Yahoo cluster, 2,100 nodes, and 72 minutes. So the guys also started within this benchmark, and the results were like this. 200 nodes and 23 minutes. So 3 times faster and 10 times lower the machines. But the most important part, without the cache mechanism working, it was simply turned off. Because when you sort data and you just have to run once for your data, the cache mechanism is actually not important. The thing that works, the thing that actually kicked the algorithm was, for example, the ones I described you before. Also, the cool thing about this benchmark is that actually they were the very first guys who actually ran it in the cloud. So you can go to Apache Spark webpage. You can actually take the code. If you have enough money for Amazon, you can run a cluster of 206 nodes and rerun the benchmark and see, okay, those guys were right because I can do the same thing. All right, how much time do I have? And the last part, I told you about, well, being reactive, right? So with Apache Spark, as you probably some of you guys saw in the previous talk, there's a separate module called Apache Spark Streaming. It allows you to do almost real-time calculations because it's not real-time in terms of Apache Storm, but it's almost real-time, meaning that it will get values from any kind of stream that you will have. You will build a small window well, you will try to read data from that input, and you will do a micro-batching. So it gives you a notion of real time. But the cool thing about it is that it can actually take the code, like 90% of code that you had for your batch processing, and reuse it for stream processing. So you have one single code base. The thing that will change is actually how you will acquire the data and what you will be doing with the data once the computation is finished. But the very main core is stays the same. And if I have time, I will show you the details in a second. All right, so I finished at quarter past noon. All right, so how it works? The very big picture. Imagine that we have a cluster, and Apache Spark will give you its own cluster, which is actually very cool if you start having fun with it, because instantiating a cluster is like simply easy. It's not the same pain as you had with Hadoop. But you can also run, if you have already a Hadoop yarn cluster, or if you have Mesos, you lucky bastard, then you are able also to run Spark on that. But let's imagine it's a cluster, and it simply doesn't matter which one. All right? We have our driver program. Driver program is your command line tool, your web application, whatever, the thing that you are developing for your clients. This is where you will actually be running calculations, sending them to Apache Spark cluster to do them for you. We have an API, which gives us API in 3 different languages, Scala, Java, and Python. As a Java developer, previous Java developer, I might say, oh my God, this is ugly. I mean, really ugly. But no, it doesn't matter. I was complaining about Flamers yesterday, and now I'm doing Flame. So, but nevertheless, you have an API for 3 different languages, so it gives you ability to choose whatever language that you like. All right, within the cluster, you have a master node. Master node was the node that you will be talking to. To actually connect to the cluster, we need to have a URI, which is like essentially a host and port. We need to pass that URI to a configuration, which takes different other stuff, but the setMaster method is the most important one. And then you will create something called Spark context, which represent, you don't probably see it, but there's a line over here to represent this line. It's a connection with a cluster, with master. And you also have other nodes which are called executors. Those are actually those guys who will be doing the work for you. So what I will do right now is I will read some file, logs.txt, and the important thing is that this file needs to be present at each of the executors. It doesn't matter if you use HTFS or GlusterFS or any distributed file system. You might be using local file system, but at that point you are responsible for having file on each of those nodes. And then we'll be doing our calculations. So the simplest calculations is count. What I want to do is count my logs. So what Spark will do will create those tasks I show you. So it will partition my data, the log files. At this point, it partitioned into 3 partitions. It will take my calculations, which is simply, at this point, just count the lines, and it will run it. So it goes to executors. Each receives this task, which telling him, this is the calculation, and run it on this part of the file. And the other one will have the same calculation, but on the other part of the file. So the calculation runs. We have our partial results. They go back to master, and the master will just basically finalize the result, or rerun the calculations for another stage, whatever. The cool thing is that if you have this scenario and you run your tasks and they go into executors, and one of your executors dies, but you had already some calculations that were being calculated, then master will actually realize, okay, this guy is dead, I don't have T3, and it will essentially recalculate only T3. It will go back to your result. It will not rerun the whole calculations. There are other optimizations that you can do. For example, master might eventually see that one of the executors is really slow. So the first two were like running like sprint fast, and the second one was like, whoa, I have time, right? So it will, for example, stop sending tasks to that node, seeing that, well, this one is performing really, really slowly. All right, so if you're going to go to the Spark webpage, you will read all about RDD. So just quickly, just so you guys know what RDD is, think of RDD as an abstraction of collection of data in your cluster. So you have a cluster with all those nodes running your computations, and you have your data in that cluster, okay? So representation of that data, the abstraction, is the RDD. So just a quick example. If I read some file from HDFS using that method, Spark context text file, the thing I have here, this logs, is RDD. This is RDD. So it's an abstraction of file that is already partitioned within the HDFS. Is that okay? Do you guys get it? Cool. Awesome. So as I said, you can read from local files as well. You can actually parallelize your collection. So if you already have some data in your driver program, some collection that you read, whatever, you can also put it into your cluster using parallelize method. All right, so let's do something with our logs. So if I lowercase all lines within my logs, operation over here, this operation map here, will return yet another RDD. So that's like RDD is immutable. It will be recalculated every time you do something on it, but if you do something on it, it will return you a new RDD. So if I do a filter with for example, look only for errors within my logs, then you will have yet another RDD. Then again, somebody might ask, what about performance? Well, basically all those operations that you see over here are lazy. So at this very point, my driver program is not talking to Apache Spark at all. There's no point, right? There's actually two kinds of operations: transformations, which give you lazy. You are just saying what you want to do without actually doing it, and actual actions who actually run those calculations. So as you will see in this example, if I run, for example, count, then this will trigger Spark and give me the number that I want to have. Demo I will not show you, sorry, because for some reasons my computer said go away, and this because I had demo actually I had demo recorded, so I thought I would be able to play it on Mac, but no, for some reason. So if you guys are interested in the demo, I will try to put somewhere on the server, so maybe you can download the demo. But essentially what I try to show you, so maybe I will just tell you guys two important things from the demo, all right, that you will actually see in the demo. The very first thing, if you, what I encourage you guys to do, if you're really interested in Spark, the entering point is really low, because all you have to do is to download Spark, the very latest release, extract the file on your file system, and that's it. Because within the bin folder, you will find a script called Spark Shell, which is simply a REPL, but it's already with imported files from Apache Spark API. And also what it does, it instantiates a cluster for you, a local cluster. So as you guys remember, I showed you that to actually connect to a cluster, you have to provide the URI, host, and port. What you can actually do is put local host instead of the URI, and Spark will instantiate it will not be a cluster. It will be a mutation of a cluster because it will run in one JVM process. There's actually a thing that's not documented in Spark. It's called local cluster, local/cluster, which will emulate real cluster. But for some reasons, they didn't put it in the documentation. I read they said, we don't want to confuse developers. I was like, I'm confused that you actually didn't put that in the documentation. But whatever. The thing is that you can download Spark, you can open the REPL, and you can start doing all the stuff I just showed you right now. So entering point is really, really small. you can later on then create your very first own cluster, or just download Docker files or LCX files, or whatever containerization or virtualization that you want, and have fun on the real environment. But for the very, just to see how APIs are working, that's simply it. Yeah.
It's also a very easy start to download types of activator.
Yeah, it's also types of activator. Yep. All right, so I have like 10 more minutes, but for those guys who are not on the previous example, I'll just simply show, because there's what we're actually talking about right now was Apache Spark Core, this module over here. And on top of that module runs a set of different modules, Spark SQL, streaming, mlib, and graphics. There's so simply no time to evaluate all of them. I thought I'll be doing Spark streaming. That was a mistake. But the most important part is each of those. If you, for example, have a Spark SQL module, and you will read some data from your structure input source, like database or JSON files or Parquet files, and you will do whatever queries using SQL that you would like to do, the result of those calculations will be RDD. So you can read some data from the database, you can do some query on it, but the result will be abstraction of data within the cluster. So you can take that RDD, do some stuff using your normal API over here, and, for example, come back to, this module, because this module also understands RDD. So that's really awesome. And the other awesome part is that if they optimize this stuff also is optimized out of the box. So for guys who haven't seen Spark streaming in the previous session, I'll just quickly show you the, also without demo, just some slides. So I will not be telling you why you need streaming, because you guys probably know why. How it works. You receive input data from your stream. Spark will collect that data, but it actually will open a window. Within the 1 second window, it will read that data that it collected from the stream, and will be doing the very same operations that you're seeing in the Spark core module, but just on this very small amount of data. So that's what I'm saying, that's micro-batching, because each of those small batch will be essentially calculated with all the same algorithms that you saw in the core module. And once the calculations are done, then results will be also sent back as a stream. So just to show you an example, what you have to do is you create something called streaming context. You also provide the window. So, for example, read within 1 second. There's a set of operations that allow you to read data from the stream. One of those operations, among many, is socket text stream. So it will read from a server on a given port, whatever comes from that server. As a result, you receive something called dstream, which is like RDD in this Spark streaming module. And you can do all the calculations that you see before. So you have almost every transformation that you saw on the RDD, almost every transformation is on this dstream as well. So I can flat map, give you a word with 1 and reduce by key. And I have my word example running within the streaming API. And as you guys see before, I have to actually instantiate this thing here to have this actually working. Because without it, you just simply said what you would like to do. You have to start it to just start reading the stream. So I have like 5 more minutes. I can take questions. Yeah. Go on.
First question is how you would test your application in Spark.
How do I test my application? Depends what you want to test. Is it like we'd like to test the result, whether calculations are correct, or you would like to test the performance?
I would say rather entire solution. So how it performs in a way that you are sure that when you put that into production it will work. I mean, first of all, you need to test somehow your software, but you can do it locally. Let's say solve this problem.
Yeah.
But then you go into the problem that whatever you have locally, if you want to replicate to the production where you have a lot more nodes, how it will perform. Is there a way to check that without really doing the, let's say, bigger job?
Well, no. You run into the same problems that you have in any distributed system. So what you can do, if you want to test your logic, then you can simply write unit tests that will run on this local cluster, and or you can do it on a small portion of data. If you want to see whether your solution scales, then you have to create a cluster and see how it performs when you add more data to it or more nodes to it. Spark actually gives a lot of tooling to see how it's performing. You can see how the data was partitioned. You can see how much time it took how much it spent in the GC, garbage collection. If you can see how much data each stage took in and how much data was actually written to I/O. So you have all those metrics that you can look at when developing a solution. But the problems like what will happen if I have more load of data, you have to deal with them essentially the same way you deal with any distributed system running in production.
Okay.
Yeah.
You say that Hadoop has a disadvantage is that every step has been saved on the disk.
Yeah.
But it gives us ability to reprocess if some stages fail.
Okay.
Is it possible in Spark to set up that every step will save and reprocess from this step?
Yeah. So you have this caching mechanism, which allows you to cache the data within the RDD, but default configuration is to actually save all that stuff in memory. But you can use, for example, you can divide it and it saves all the data on the disk. You might just say, save that data, but please save it on the disk. And it will be saved on each node, the part of data that each node was actually doing the calculations on. So you have the ability to choose whether to be, instead of being forced to. The thing is that if you have a problem on RDD, it will be, if your RDD fails, then you don't have to worry about it because Spark will recalculate all that stuff for you. That's why RDD is called resilient. But
I don't have to worry, but the problem can be if it's very expensive calculation on the step, and I want to recalculate again.
yeah, so that's why you have this caching mechanism. But the cool thing is that actually you don't have to save it to disk, because if its data is small enough to be saved in your memory instead of I/O, then it will be blaze fast, right? Oh yeah.
So just on the side, if I have a problem like getting the count of the unique logs, something like that, can I also getting count of unique logs?
Oh, yeah.
Is that also easy way to do with Spark?
Yeah. There's a method called distinct. That's it.
But then it has to do. It still has to. I mean, the uniqueness has to be done like globally.
Yeah, exactly. That's but you still have to read all the data, right? Essentially, when you run your calculations, the data has to be divided into a cluster. It has to run through and look for distinct values. So. Yeah. So essentially, I'll just give one advantage if you guys playing with Spark. Read the API. There's like 30 methods. It's actually nice to know all those methods because don't do my mistakes. I read 10 and I thought that's enough. What happened is that other 20 were the actually ones I should read about. So yeah, like if you guys decide to play with Spark or try to go with production, know your API because there are some methods that will do some stuff better for you.
You showed us here.
All right, sorry.
You showed us the graph, and it seems that Spark outperforms MapReduce, no matter whether you have a lot of data or not. Is there a case when you prefer MapReduce to Spark, or do you consider it some kind of silver bullet?
The thing is, I do not have experience of Hadoop, so I cannot give you the full answer. I don't believe in golden hammers. I think, for example, if you have like vast amount of data flying in, and your issue is how fast you are, and you don't care about batch computing, then maybe I would switch into Apache Storm instead of Apache Spark, because you have to remember it not always gives you the best performance. It gives you the unified API that you can connect with MLab, with machine learning, with the Spark core, things like that. So there's always a trade-off, right? The Spark gives you this unification, and it's actually a good thing if for some set of problems. Maybe for majority of problems, but not for all. So I would say, answer your question, in fact, I don't know with Hadoop, but for example, with Apache Storm, I would consider actually thinking about it if you have many streams actually connected, many clients to your system, and you have to be very performant.
You mentioned problem with Hive, which is essentially abstraction leaking. Is not there a same problem with Spark and with all this abstraction?
No, because it's done better. No, actually, if you guys they did some research. It's another good thing because it tells something about our industry. But they did some research, and they were able to do better calculations within Apache Spark SQL, than when they gave core API to developers to run the calculation without using Spark SQL. So they rethink, because so Apache Spark at the very first moment when they introduced the tool to the industry, they knew like 90% of companies that they're saying that they're using Hadoop, they're not actually using Hadoop, they're using Hive. So they knew if they need to show the performance boost, they will have to have some ability to actually run Hive queries on a Spark system. So what they introduced was a Spark Shark, which was like they did some workarounds around Hive, gave like a small abstraction around it, and called it Shark. And it performed better than Hive, but still it was crappy. So after initial phase, they rewritten the whole thing, taking into consideration that they are doing this for Spark, and they put some optimization into that code. It performs better. Simply as that.
Okay, but on some level, it's maybe same problem.
No, the problem of MapReduce is essentially you are stuck into map and reduce to those phases, and that's it. With Spark, you can think a little bit about it. I will give you an example. For example, imagine a group by method. What you would like to do, for example, is you have your data. You want to group by some key, whatever. You have your users. They have some ID, and you want to maybe not some users, maybe some logs or whatever, and you want to group the collection of data with the given key. Having that group, you just simply want to reduce. Okay, so like flatten all the data. So at the end, you will have your key and reduced value. All right, and you have the API to actually do group by and then reduce. Okay. But what it will essentially do, to group by, you have to shuffle, because all the data will flow through the cluster. And on each cluster, you will have each data for each node, and it will be reduced locally. But this phase over here has to put all the data, all your 1 million, 1 trillion values through the cluster, just to be reduced and output to the client. There's also another method called aggregate by key. What it will do, it will first reduce data on each node in parallel. So you will have reducing being done on each node, and which will create like partial results. And then it will send partial results to the nodes. So the shuffling will also happen, but with a lot of less data in it. All right? And then the performance boost between the first solution and the second is enormous. But so it happens that you have a richer API. With MapReduce, you cannot do this. You have to go with the very first solution, right? So that's probably that's why they can outperform Hive in the. There's actually, I don't have it in slides. I had in previous presentations, but there's like the same queries, the same SQL queries done in Hive and in Apache Spark SQL. and the results like Hive, Spark. Sorry. Tough luck. Any other questions?
Okay, my question is about this example where one executor died.
Yeah.
Okay, we have one remaining part of work which we have to execute once again, and two remaining executors. So let's say that, let's assume that this part of work is the big one. Would it be possible to split somehow this part of work and execute in parallel? Using this both executors.
Yeah, so some of the methods within the API gives you ability to repartition the data. And there's also a method called repartition, which basically repartitions the data. So yeah, so know your API and you'll be fine. But yeah, you have to remember that repartitioning data is again a shuffling. You can actually do it if you. There's another method, I cannot remember how it's called, which will actually will repartition without doing the shuffling, but only if you will be making your partitions bigger, not smaller. If you're doing your partition smaller, then the data will flow throughout the cluster, but sometimes it's better. I saw that on Spark Summit last year, they're just showing an example that they had this computation that was really, really slow, and they did some optimizations. Eventually, they introduced more stages, because essentially there were 2 stages. At the end, they had, I think, 4, but the 4 were optimized. One of the very first stages was repartition, the thing that you are asking. And repartition allowed them to actually speed the things up. More stages, but it was quicker.
Okay, I think we have to skip the rest of the questions for the...
Just don't be shy. Ask me questions outside. I'll be happy to answer them.
Exactly. And there will be a keynote now. So the keynote will be on the other side of the building, so in the ledge room. And we have like 7 minutes to start. Thank you, Paweł.